Hey folks, welcome. We're going to try to do 100 slides in 40 minutes, so we may not breathe for a little bit, but if we don't have time for questions, we'll either go in the hallway or do the wrap room, so let us know. So let's get rolling, hopefully. And here we go. Sweet. So this is a talk about the evolution of Secure Shell. So an overview of the SSH ecosystem, which is way bigger than just SSH and drop bear, what's changed, what hasn't, some really new and interesting attacks, and a little bit about the fragmentation of the OpenSSH code base and deployments. And then we're going to talk about some code rewrote, which we call Shamble, which is a fun way to drop random shells out of devices with SSH. And then because it's blackout, we're going to tell you how to defend it too. So with that, we'll get started. So in the beginning, 30 years ago, there was SSH. So Tatu Yolonen created SSH v1 back in 95. It was forked into OSSH. It was forked into OpenB's OpenSSH, then became OpenSSH Portable. Later on, PKIX split off, and then you've got drop bear. So there's a lot of different versions of SSH based on OpenSSH, but then you also have drop bear as a separate code base. In addition to those two, there's a long tail of other stuff out there. So if you look at internet-facing SSH daemons, it's mostly OpenSSH and drop bear, like 90%. But you have this long tail of other oddball stuff. LANCOM, the HP ILO, MBSSH, the We Only Do stuff, the Zycells, the NetScreens. And even though these only make up about 10% of the stuff you see on the internet, they're pretty important. So a lot of the not OpenSSH stuff out there, like your firewalls, networking, and storage devices, your Ciscos, your NetScreens, your AdTrans, they're all running custom SSH implementations that have nothing to do with OpenSSH, or at least haven't for a very long time. At the same time, a lot of your OT and ICS equipment, things like your Siemens, your NetPower, Mocana, et cetera, those are also running their own SSH implementations, and again, not based on OpenSSH. So there's a pretty big attack surface of things out there that are not OpenSSH, but they are running SSH, and that's where we're going to focus a lot of our time today. Separately, we've seen our friends like MoveIt, for example. They actually have an SSH implementation as well. That's based on IPworks we'll talk about. And there's also a lot of these source code forges like Git, Gerrit, and so on that have their own built-in SSH daemons through libraries. So let's see, going in the right direction here. SSH is everywhere. It is the second most common admin protocol if you include HTTP as the first one. It is more popular than RDP, than SMB, than anything else. It's how the internet is admined. So without SSH, there pretty much is no admin. Everyone uses SSH in some form, even if it's through things like SSM or through some other mechanism to transport it. It's enabled in every cloud provider by default. It's part of every major OS. You can find it in embedded devices, servers, and mobile. So SSH is pretty much everywhere. SSH protocol really is two phases. You've got your clear text stuff, like your version exchange, your key exchange init, things like that. And then after your key exchange, after your Diffie-Hellman, then you have all your encrypted stuff. And your banner, if you will, your authentication, all that happens in the encrypted channel. And that becomes important when we start talking about the state. So you've probably seen the SSH banners before, things like SSH-2.0, OpenSSH-98P1, et cetera. Obviously, there's the version of the protocol, there's the name of the product, and there's a comment, which is often the package name, and you also get a list of like ciphers, MACs, things like that. So we talked a little bit about this, but basically, after you've gotten the version exchange, you some sort of key exchange, either Diffie-Hellman or similar, and then you go into the authentication phase of like passwords or public keys or things like that. What's interesting about this and kind of fun for the research, I was trying to figure out like how does pub key authentication prevent the server from relaying to another server? Well, ends up the entire signature blob signed by the public key starts off with the key exchange negotiated session ID, which of course is tied to that host. So if you're ever wondering how that works, that's how it works. So there's a lot of stuff in SSH. You've got interactive shells, command execution, file transfers, TCP forwarding, Unix forwarding, X11 forwarding, agent forwarding, you name it, and they all go across the same socket. And we're going to talk about how some of those things make things more challenging. So what's interesting is that SSH, especially recently, has been treated more like TLS than it has before. So TLS, as you know, is what makes HTTPS, secure web work. And a lot of folks are now using SSH as if it was TLS. So what's, the main differences, though, are that SSH, of course, doesn't typically have a certificate authority. While you can set up SSH certificate authorities, it's not the most common way to do it. Authentication is actually a core stage of the protocol compared to TLS. And it has this multiplexer kind of built into it for things like channels and sessions, things like that. Another important difference, and this is important when you think about things like the Terrapin attack, is that when SSH is doing its key exchange, the first cipher sent by the client is used that's supported by the server. Not the best, always the first. And that's why the Terrapin attack was so effective. And we'll talk a little bit of that later. What's interesting about this, though, is the compliance standard. So compliance typically covers TLS very well. You must use these algorithms, this stuff, et cetera. And they sort of kind of talk about SSH in the sense that if you use the same algorithms and ciphers, you're OK. But no one really talks about host key management. And the key management part is actually really important to the security for SSH because there isn't typically a central CA. So with that, let me hand off to Rob to talk about what's new.
Thank you, HD. So what's new in SSH? It's a protocol that's everywhere. It's evolved over the years, and it's got a well-defined mechanism for adding extensions. So most of those extensions are dealing with new protocols, new key exchange mechanisms, signing algorithms, things like that. But you do also get, and also some post-quantum stuff, which is super cool. But then you also just get some interesting protocol extensions like ping and pong or host-bound keys, lots of tunneling stuff, super useful. Also, over the years, we've seen new authentication mechanisms added to SSH. Multi-factor authentication is much more common now, much more available, much more easily integrated. You have challenge response and keyboard interactive. I always find it funny. So keyboard interactive is designed to do lots of potential authentication algorithms, but 99% of the time, it just ends up being passwords. But still, it exists, and it's there now. And you can also have these the beautiful YuBi keys and other external agents, hardware keys, and you can even specify that those keys need to be verified, have a PIN, have a user present, things like that. Super, super useful. And you can have, as HD mentioned, centralized SSH authentication with certificates. And these are amazingly powerful. And it's something that I wish more people use, because you can really do some very impressive things with it. And you can also use SSH certificates for host authentication, things like that. And then something that we've seen in our research that's come up just over the years, SSH has always had these pre-authentication banners, but they're significantly more common now, especially on these long tail of devices that we were talking about, the routers and things like that. And there's an immense amount of information that is disclosed pre-auth. And here you can see an example of the extensions and things like that. And this is how they're advertised. You can see the ping at ssh.com and all that. And these are advertised and negotiated upon during that initial protocol negotiation phase. There's also the, and this is OpenSSH specific, the per source penalties directive, which I highly recommend that you use. It's been implemented to prevent or mitigate brute force attacks. And you can basically define a source as a network address or a range of addresses, and then penalties can be, block that or slow it down, things like that. That's becoming more and more popular. And then I also love SSH keys are now public identities. Your public key is, mathematically speaking, supposed to be public. You're supposed to put it everywhere. But people, I think, don't realize, especially with the advent of these large open source projects, that your GitHub, or that your public key is your public identity, right? It is your passport, identify me. But you can go to GitHub, you can go to Launchpad, you can get your public key, and people will know who you are. In fact, here's HD SSHing into whoami.filippo.io, and in fact, they know who he is because of his SSH key that was scraped from GitHub. SSH has also become the sort of de facto standard in secure file transfer, and it's very common in these border gateway devices where you're uploading documents across secure domains. So like when you're uploading your medical records, you're applying for a mortgage, things like that, you might end up using SFTP. And this is great because it's a much more secure protocol than we used in the past, but it also makes these things extremely high-value targets. And then this is my favorite slide of the whole thing, because I love terminals. I've written more terminal emulators than I can count. It's just great. Come talk to me about terminals. But SSH has caused a renaissance, or more accurately, there's been a renaissance in terminal applications. And it's just great. You can see there's Star Wars on the terminal. That's actually pretty old, but you can get to it via SSH now, not just Telnet. ASCII art is coming back. And you can buy coffee using SSH. But what's neat is that this is increasing the usage of SSH. It's causing this renaissance at the terminal, and I just love it. But that also increases the amount of exposure, which HD is going to tell you about.
Cool, thanks, Rob. So just to set the stage a little bit. So one, we mentioned Terrapin earlier. Fabian's doing a talk tomorrow. I would definitely recommend checking out an Islander FG level 0. Breaking SSH channels integrity by sequence number manipulation. It is fantastic. It's a really neat way to use some cool crypto primitives and a man-in-the-middle attack to do terrible things to SSH. So I recommend checking that out. This has really been a banner year for SSH in general in terms of being an exciting year to operate SSH. We're probably all very familiar with the XEUtils backdoor, how this multi-year campaign backdoored OpenSSH through the systemd patches of RHEL and Debian, and it was a really neat backdoor because it was a nobody but us backdoor. It was tied to the attacker's specific key. And it was caught at the very last minute by Andres Freund, and he noticed that SSH was using slightly more CPU than it should have, and that kind of unraveled the whole thing before it made it out to the stable distributions, but it did ship into the rolling distributions. So definitely exciting times in SSH. Not to be outdone, of course, the Qualys threat research team is amazing and did, yet again, a fantastic job of pulling a rabbit out of a hat with a remote root exploit for OpenSH that applies to literally everything, everything between a huge range of versions. And this is, pretty big deal. Like, it's pretty hard to get unauthenticated remote root code execution OpenSH, especially given all the different things the team has done to protect against it. But because it's a signal reentrance bug that's effectively a regression of a previous fix, the signal reentrance happens to the parent process, which runs at root, not as one as its privsept. So an incredibly cool exploit. They managed to exploit a 32-bit Linux OS in about 6 hours, and they estimate probably weeks or months to pop a 64-bit machine. So if you ever have a hardened vendor appliance and you want to spend 6 months grinding keys on it to get a shell and you haven't updated SSH, well, there you go. So very few folks have actually applied patches to OpenSH for regression yet. Separately, a Solar Designer found a related bug that only applied to the Red Hat build of OpenSH, and that was limited to the non-root user. So exciting times for sure. And then lastly, this is a fantastic work by the Watchtower Labs team. They were looking at the most recent MoveIt vulnerability, and there's so many, but the most recent one was hilarious for many reasons. They've realized that it's actually a vulnerability in SSH daemon itself. So MoveIt, including the web interface, also has an SSH implementation. It's based on the IPworks library. They identified the fact that anytime a public key is being processed from an attacker or a user, the SSH daemon is treating it like a file path. The giant binary blob they treat like a file path, including a UNC path. So you can do forced authentication to a remote server, all kinds of terrible, awesome things. They found this amazing way to exploit it by basically injecting a key into the log file, making it trust itself. Like, it's an amazing post. I recommend checking it out. But the really amazing thing about this is that they found the vulnerability. They identified the vulnerability in MoveIt, of course, through the reversing the patch. But then they identified that it really was part of the IPworks library, which is used by all kinds of other vendors for other products. So who knows how many other products out there are still vulnerable to this particular bug because they use the IPworks library, may not have updated their SDK, or the license is expired. So fun times. With that, back to Rob to talk about what hasn't changed.
So things that haven't changed in SSH, it's still running on the internet, right? It's still running over IP. You can still identify the operating system through fingerprinting the TCP stack, which is, great. You still get the clear text exchange for like server version negotiation, things like that. You still get the advertisement of the key, all this pre-auth stuff, the key exchange, the algorithms that are available. You can use that. And like we mentioned earlier, the banners, which are just so much more common. And then for the enhanced authentication, the questions that they're asked, the wording, things like that, can all be used to fingerprint what you're talking about. And it's interesting because, as HT said, there's been a huge amount of work to secure SSH before auth. But because it's so full of features, because they want you to use it for a lot of things to keep things secure, it's got a fairly large post-auth attack surface. You've got channels, you've got pseudo-terminal management, all sorts of things, agent auth, break commands, X11 forwarding. And so if you actually get authenticated, the attack surface is much, much bigger. And then it's still, because it's designed to be remotely accessible, there is a default exposure to brute force attacks. This is somewhat mitigated by fail to ban and things like that. It's a third-party stuff. And then the per source penalties will help a lot. But SSH is a relatively compute-intensive protocol, and some of these devices are relatively, not particularly beefy. So it can consume a significant amount of CPU in these situations. Host key management has never been good, and it hasn't gotten much better. Host keys are a separate key pair that's used to uniquely identify the machine, not just a user. And those are, they're very often duplicated or burned into VM images, and so you'll have like 1,000 machines with the same host key and things like that. And they're very rarely rotated, because rotating them can often break workflows in fun and amusing ways. And SSH is still used as a transport layer. It's still used almost as like a little miniature, rapid, quick-to-set-up VPN. And it's great, and you should definitely use it, but it's still something that is quite commonly used. And now, to get into some really neat stuff about how this can be broken, I'm going to hand it back to HD.
Thanks. So, folks who are familiar with public key authentication, the idea is you have an SH key, you add it to your key ring, your agent, then you authenticate to a machine. You may have agent 40, you might not. But how it actually works behind the scenes is a two-step process. You start off saying, hey, server, would you accept this public key for this user? It says yes, and then you sign a blob, starting off with the KEX session ID, and then a bunch of other fields in it that prove that you own that private key. And it says, yes, you successfully signed that blob. You now own the private key. There you go. The caveat, of course, is that if you don't have the private key, you can still do the first step. And there's a comment in OpenSH that says, hey, this is like fake a reply. Should we actually be doing this? Is this a security concern? But it's been there for 10 years. This is considered not really big a security impact. There's a Metasploit module that does this half authentication pub key scan, where if you have someone's public key, you can see which servers accept that public key even without having their private key. And because, that you can kind of see where this is going. So if you wanted to, let's say, test every server on the internet to see whether a particular public key was accepted for a user, there's a couple steps you'd want to take, or 3 steps. One, get a list of all the servers on the internet. So quickly, ZMap, mass scan, whatever you want to use, mmap, pick a database to dump it all from, whatever you like there, and then go build a giant database of all the keys you want to hunt for. So you can grind through all the GitHub stuff through BigQuery, crawl all the keys, build the database. You can pull them out of Launchpad for all the folks using the Ubuntu Launchpad platform. It's pretty easy to crawl those. And then the Bad Keys project by Hanno Block did a great job of collecting all these compromised keys that could be used as well. And then lastly, you want a list of usernames to try for each key. So this could be your standard cloud defaults, could be the comments from the person's key in GitHub, which usually indicates what their default username is, and so on. So you put this recipe together, and we go hunting for Gia-Tan. So we thought it'd be hilarious that if Gia-Tan, whoever this person or thing is, decided to backdoor OpenSSH and target SSH, so we're going to use SSH to target Gia-Tan. So we grabbed Gia-Tan's public keys off GitHub, and then we turned around and scanned the entire internet with a bunch of default usernames to see what server on the internet would accept the Gia-Tan public key in hopes of doxing the Gia-Tan person by finding their home servers and other machines they're using. So we thought it'd be a fun use. So putting it all together, we created the public keys, got the public keys. We wrote a little half-off scanner in Go just because we need something a little bit faster than the Metasploit for this because we're doing a crap load of systems at once. We called it Shamble, and that's where we started this whole thing back in the executils backdoor. So we ran Shamble on all the hits, and we murdered this poor DigitalOcean box for days because it requires a lot of CPU to negotiate 43 million SSH connections continuously. But we did it. It was fine. So. But the key thing here is we found a lot of stuff. We found tons of hits for Gia-Tan's public key, and we're like, oh my god, we got him! And then we started digging into it, and it's all freaking false positives, it's buggy servers, it's just with memory corruption. We found services that would accept every other public key, every third public key. They were just dying with out of memory conditions, all kinds of terrible stuff. So we reworked the tools, we added detection for any pub key, we did some false positive mitigations, we added all this crap to it, and then we still didn't have a Gia-Tan. So whoever the Gia-Tan group was, their OPSEC is perfect, because we could not find anything. However, what we did find was 50,000 shells. So that's what we're going to talk about instead. So we didn't find what we wanted, but we found crap loads of bugs, so we're going to talk about all the fun bugs. And that led to this talk. So just heads up, law enforcement, we are not Gia-Tan. Unfortunately, as part of doing that scan, we put the public key hash of Gia-Tan's key in everyone's logs across the whole internet repeatedly. So if you see it us, I swear we did not backdoor executils. We're not that cool. And so let's say you wanted to test public keys, but you want to do it faster. So we talked about taking a small number of keys, like Gia-Tan keys, and trying against a lot of servers. What if you want to go the other way and try a whole lot of keys against a single server? So I want to find out, for this given server, which person on GitHub has access to it effectively. So if I have all the GitHub keys, let's say 5 to 117 million, depending on which database you use, how can I figure out which person has shell access to this machine? If you want to dox somebody, for example, OpenSSH defaults to 5 authentication attempts before it disconnects you. So if you have more than 4 keys in your key ring and you try to SSH to a machine running OpenSSH, you get disconnected before it gets to the right key, and it's really annoying. So that's why you can't really have more than 4 keys in your SSH agent typically. But not all servers consider pub key test as an authentication failure. So 10% of all the servers in the world do not count any pub key test as an auth failure, including drop error, which is the second most common at 12, 15% of the internet. So if you look at all these other daemons, you got Global Escape, all these different commercial MFT programs. None of these actually prevent any kind of rate limiting of pub key testing. So you can just grind them all day long. So we did that. So we built so as part of Shamble, we built this pub key hunting tool to go find Gia-Tan. Then we're like, hey, we can actually just make this thing turbo mode key grind. So you can take the entire, in this case, we took the 2018 GitHub key database of 4.6 million keys, and we tried all of them against one little drop error box in 7 minutes. So you can very easily dox and figure out, is there anybody whose key I have that has access to this server with this username very quickly on a machine running anything other than OpenSSH effectively. Only OpenSSH actually limits the pub key attempts. So in this case, we did 10,000 per second, but this is 10,000 per second on a single connection, and most configurations allow between 5 and 15 connections. So you can do 100,000 keys per second, and the really cool thing is it doesn't even use very much CPU. Drop errors, even on an embedded device, isn't really using much. This is a very effective, very useful doxing attack, anything you like. So we do the exact same attack, but this time against an OpenSSH box. You'll notice that we only did 132 per second because we're having to constantly reconnect. And each time you reconnect, you have to do the key exchange, and it's kind of slow and it's annoying and things like that. So there's a turbo mode key grinder. And now we're going to talk about something a little bit different, which is authentication bypass bugs. So SSH has this strict kind of state engine built into the protocol. Not only are there different individual states like key exchange, version exchange, pre-authentication, authentication, channel, shell, et cetera, but the message IDs that you're allowed to transmit within each stage are kind of fixed. There's a range of IDs you're allowed pre-authentication. There's a range of IDs post-key exchange you're allowed to say before authentication. Then after authentication, there's a range you're allowed to use. So most of the SSH implementations will use the ranges of those values to prevent you from even sending a packet that it doesn't expect. Separately, OpenSSH and Dropper also have a giant command state table, like a function table basically, where they're rewriting which functions are even callable based on what state you're in. So you can't accidentally get to authenticated stage because they just don't even have a function pointer there. They just make sure it's very hard to screw it up. So you've got this great SSH protocol stack, and it mostly kind of works, except people screw it up, of course. So there's a really cool bug in libSSH back in 2018 where libSSH is both a client and server library, just like Dropbear and OpenSSH. If you told the server that, if you sent the server the authentication success message that you normally sent by the server back to the client, it'd be, OK, you're in, and now you have a shell. It's great. So we thought, like, OK, that's a cool attack. So in this case, you just sent this one unexpected message, and you were accidentally authenticated. We decided to try that with every single state of the protocol. So we built inside the Shamble code, we had it at every single phase of authentication, attempted, pre, post, auth, mid, et cetera. We just said, hey, give me a shell now. How about now? How about now? How about now? And it started raining shells on us. So we thought it was really cool. So some of the bugs we found, there's only a few here. There's a few more that we're still chasing down. But digi-transport, ICS gateways, little gateway router thingies used for a lot of industrial control systems. They had a bug where there's an uninitialized variable where if nobody else had successfully authenticated that machine since it rebooted, you could just log in without a password using the straight transition bug. So that's baked into Shamble. We got a demo of that. A lot of Realtek ADSL routers have the same bug. And we found a few Panasonic Ethernet switches, the same thing. We just like shell right in, bypass all the password authentication magically just by throwing these session requests between different states. So an example of that, this is the Neterbit NSL. These are really popular in Iran for some reason, and these are based on the Realtek chipset. We found some of the Realtek chipsets running 2023 firmware still vulnerable to it, but we don't really know who to even talk to about it because it's all within that. So you'll notice there's an interactive Shamble command now. We're actually able to use the SSH protocol itself to mess with the servers after we've got into it. But yeah, strip, auth bypass. Here's the same thing for digi-realport devices. We're just basically running Shamble saying, give me interact with the first shell, and you got a shell. So not particularly exciting, but it's always nice to get free shells. Cool. There's a category of devices that instead of doing authentication in the SSH protocol, they let you authenticate as anything. And then once you're authenticated, then they give you an interactive prompt. So please log in. So effectively, you SSH in, it magically authenticates you in, and then it says now please log in, and you type in root or whatever your password is, right? This is a really bad idea because there's so much stuff you can do in the SSH protocol at that stage, in that particular state, that it's hard to prevent attacks. There's so many things that SSH does to prevent you from even getting to that phase that if you give somebody an interactive process, you can now send signals to it. You can like mess with the PTYs. You can do all sorts of environment control stuff. So we started messing with some of that. So examples of devices that do post-session authentication. Juniper routers, Ruckus access points, and Sonic walls are just a couple examples offhand. There's probably about 1,000 of these things we found out there. And they're pretty fun to mess with. So we found this really simple, dumb bug in Ruckus wireless access points where if you're starting to log into it, you type in, you see in the little demo here, we're SSHing in as root. You see first we authenticate, so SSH is now asking, SSH automatically authenticated, and now it's asking us to log in manually. In the password field, we're just typing in $parentheses and PS AUX, and we're getting the full PS as root pre-authentication. So super easy bug, and we found about 900 still exposed in there that are unpatched. But the vendor technically already patched this, but there's never a CVE for it or security note. But why did this bug live so long? How come this bug even got there? Well, it ends up no one ever tests the shell at the end of the SSH shell. It was so far buried in the protocol that no one really ever looked at that phase of it. So we found a lot of like really trivial bugs just because no one bothered getting that far into the state to mess with it. So one last thing that's a lot of fun to mess with is you can send any signals you want through the SSH protocol. And OpenSSH is smart and says, well, I'm not going to let you send some of them. You can send like a sig kill or a term or a hup or whatnot. But Dropper lets you send anything you want. You can send a sig-seg-v. You can send a sig abort. So we talk about regression, big signal reentrance. This is signal whatever the hell you want. You can just bang signals into a process all day long. So this is a really funny one. This is a login prompt that's post-authentication. It says, please log in. You say signal-seg-v, and it goes, ah! It's great. And it just like crashes. So it's a really fun way to like core dump a random login process. And we're still doing some research to find ways to actually get shells out of it. But it's a really funny way to attack a post-auth login sequence. And with that, I hand off to Rob to talk about forwarding.
if it were dying, it wouldn't write IE, it would just say IE, but no, yeah, maybe it was dictating. So SSH connection forwarding is part of that post-attack surface. And it's pretty interesting. You know, SSH allows you to forward IP connections, TCP connections across and through machines. And we found that it's not super duper common, but it's actually it's more common than zero. We actually have a live, well, not live, we have a recorded demo here of a ION network service access point. And you can see that oftentimes it might not allow unrestricted forwarding once you get in, but it does allow forwarding to a few places. You can see it fails a few times, but it does let you loop back and connect to services locally running on that thing. So it's a way to bypass some information there, which I always found fun. And then we were talking earlier, by the way, I want you all to appreciate the pun. Check out Git. That was my greatest contribution to this talk. So check out Git. Git is uses SSH as one of the supported transports for moving your source code around, things like that, checking out. And there's been this renaissance in Git in code forges that are running embedded SSH servers. And for example, there's GOGS, Git, for Jeho. I think I'm saying that correctly. And they're usually pretty good about filtering environment variables and things like that. But for example, there was a bug in Go 119.3 and prior that did allow you to do environment variable injection just by inserting a null byte. It didn't check correctly. So that was fun, and so you can get some interesting things there if you do allow Git protocol to come across. And then there was also the env command injection with GOGS. So SSH allows you to set environment variables. Locally, you can say, please set this environment variable, and it will try to set it. And you can filter what's allowed to be set and what isn't. But GOGS, which is a Go-based Git forge, was running the env command in response to getting an env request. And you could set a environment variable like -x equals whatever, and git and then run whatever command you wanted. That's not patched, and I think we're kind of considering maybe you should not use GOGS in that case. But a lot of these libraries that implement embedded SSH servers, they leave it up to the client of the library to select what environment variables should be allowed through. And so they often just allow anything through by default. There was a really fun one. This is a CVE that we just got published in the SoftServe forge, which is a really beautiful Git thing that lets you create repositories via SSH and all that, but it wasn't filtering environment variables, including LD preload. So here you can see we're checking in some very innocuous files called shellcode.so, and we are pushing it up to the server, git commit. I am apparently a very slow typist when I'm in GIF form, and we're using git LFS in this case just because it leads to predictable file names on the server. It's not actually required. And then you can see we're just calling with LD preload with our file name. And look at us, we are now just running arbitrary code. Yay, always fun. So filter your environment variables is the point there. And like any other protocol, SSH has fragmented, and HD would love to tell you about it.
So part of all this is we started auditing all the code, right? So I had 50 different repos of SSH code in my file system, a bunch of reverse engineering of various commercial libraries. And one thing that was particularly interesting was the split in OpenSH. So we'd like to think of OpenSH as being just OpenSH, but in reality, OpenSH is the one based on OpenBSD. It uses OpenBSD function calls. So what we use instead is OpenBSD Portable. OpenBSD Portable is designed with a compatibility layer that runs on Linux, Mac OS, things like that. So the patch sets that different OS vendors have applied to OpenSH go from almost nothing at all, being very light, to massively different. So there's not just one OpenSH out there. There's a million different variants based on what people have done to it. So Apple actually has the least butchered version of OpenSH. They did some very light patches for endpoint event logging, for keychain support, things like that. Other than that, it's pretty much bog standard and it's great. So it's actually pretty awesome. Now, if you look at Debian and Ubuntu, they have 36 different patches on top of OpenSH. And you talk about how many bugs are in how many lines of code. Well, these are bugs specifically in the Ubuntu and Debian versions of OpenSH, not upstream. So they get a little bit less scrutiny, and a lot of those things are a little more difficult to secure because they touch much more parts of the system. So same thing with Red Hat. They've got 60 different patches more than 60 patches they've applied on the OpenSH source code to make it compatible with Red Hat. And both of these are XDutils backdoor compatible because they link to systemd, and that's how they were exploited basically. There's also this thing called PKI-X SSH. This was forked from OpenSSH back in 2002, and it was designed to support X509 and FIPS and things like that. Well, it's kind of diverged significantly from the rest of the OpenSH source code. While it kind of sort of follows the changes, there's some diffs where in one case, an if something happened in OpenSH, it became an if not something in PKIX. So it's a little bit strange that sometimes the changes didn't directly mirror it, and that seems like there's maybe some risk there because it is so different. Funny enough, the PKIX SSH implementation was still vulnerable to the regression bug too, even though it was separately implemented based on when the code is forked. And the last one we talk about is probably the funniest one, and kind of we'll use a little bit of a punchline here, is the Microsoft Windows, OpenSH for Windows, 350 files are changed. They ripped out tons of stuff. They got rid of root support. They replaced fork with subprocesses. They replaced authentication with the LSA calls. Like, it's a very different beast than OpenSH itself was. And we decided to dig in a little bit deeper and figure out, what's different about it. So one, OpenSH is on by default on all of your Windows 11, Windows 10 desktops, which is pretty cool. Now, the client's already on there. If you want to enable the server, you enable the feature and then turns the server on. But people are actually doing it. Like, SSH is actually a really great way to use PowerShell. It's way better than WinRMI or CIFS or anything like that, right? So if you had to pick a protocol to transport over, it's probably, at least you're using SSH. So you want to see, well, how different is SSH on Windows compared to everything else? Well, first off, and this is a great reference that was called out by DJM, is that OpenSH for Windows sends all of your stuff back to Microsoft by default. Now, let's be really clear. Like, this includes things that are encrypted in the SSH transport, like your authentication methods, are sent back in the telemetry calls back to Microsoft by default. In this case, the version is being sent back. So the version of your server during an initial connection is sent back to Microsoft. Now, that doesn't seem like a big deal, but keep in mind that version includes your client version too. So Microsoft knows not only that you're using SSH on Windows, but which clients are talking to it in terms of which client versions. Are you vuln scanning your system? Well, they know every time you run Nessus against your Windows server running out OpenSH because that is a very particular SSH client version getting sent back up. So it's a massive information leak going straight up into Microsoft telemetry for OpenSH for Windows. So I don't even know how to disable that. I think you just don't use it, unfortunately. The other one that threw us, though, is there's this really tiny function in OpenSH that's really critical and really important. It's the timing safe bcomp. It's designed to be a timing safe byte comparison between two cryptographic or otherwise sensitive buffers to make sure they exactly match without leaking information about how long it took to compare them. So effectively, it goes through the byte buffer A, byte buffer B, does XOR, and then compares, OK, are they different at the end, and that's that. So really small function, like 4 lines of code, 3 if you don't count the variable initialization and the return. There's not a whole lot here to break. It's timing safe, it's efficient, it's secure, it's been in OpenSH for 14 years, something like that. It's a great piece of code. Then there's the Windows version. So Windows version decided to make it CRLF compatible. There is no such thing, right? So they took a function that was very secure and 4 lines of code long, and they added 2 lines to it that effectively backdoored all of OpenSH for Windows. So it's no longer timing safe. It's a 1-byte out-of-bands memory read, and it's an unequal byte match. And this function is critically important because it's used by everything in OpenSH. It's used for every single SSH encrypted byte buffer is actually compared to see whether the signature matches through this encrypted check. If you happen to have an encrypted blob that happens to have a backR backend, it's now reading 2 bytes outside the range of memory. And since the range of memory at the end of that string is all typically zeros, you can now basically bypass part of your crypto check. You just lost 2 bytes of entropy rate, or 2 bytes of randomness, right? So it's really hard to exploit in a lot of ways because you have to, there's 2 buffers involved, and an attacker typically doesn't control the buffer that actually triggers the bug. But there are ways to make it hit, and we were able to brute force it enough times to make to at least demonstrate like a 1-byte out-of-bound read. Not super exciting, but it was just terrible that this happened, especially for an organization that claims to have 3,500 security professionals and to spend $1 billion a year in security. Maybe don't backdoor the most important function in OpenSH. Just saying. So Microsoft gave us a nice reply saying, that's nice, thank you, we won't fix it. I'm like, OK, well, you didn't fix Terrapin either, so I guess we're done. Yeah, so that was a fun diversion. We're going to talk a little bit about the code we wrote. This is actually live right now this second. We just shipped it. So if you go to shamble.com with two S's, it'll take you to our GitHub repo or to a landing page, and you can just check it out and play with it. All the attacks we just showed you are live. So there's a bunch of ODE in there that you just kind of throw it at some random servers. We love just throwing this stuff at random stuff, seeing what falls out. But what Shamble is basically a research tool. So it's a practical one that you use it for assessments, but it's also just a research tool to play with and extend. We forked the Go X Crypto SSH library to make it do all kinds of terrible things while still being easy to patch going forward. So it should be easy to maintain that. It does some really neat attacks against authentication, a lot of post-authentication attacks, like Rob was showing, like the ones against GOGs, things like that. Those are all baked directly into the code. You can just run them as out of the box. There's some nice pre-authentication state transition bugs there, and then post-session enumeration of like, OK, we've got a session, but how can we break out of the shell and do restricted stuff? We didn't talk about it today, but we also added some timing analysis code to it, so you can do things like, is this user valid based on timing of doing pub key versus not pub key? Funny enough, the way that OpenSH and Dropbear prevent timing attacks is they do a SHA hash basically of the username, and they do deterministic delay based on the SHA hash through a bunch of math ops on it. So if you check how long does it take to log in as root versus root 1, there'll be very different timings, but it's because of the SHA hash key seed of the timer, not because you're actually getting a timing attack to work. So there's a bunch of built-in checks. We added a crap load of stuff to it already, so just out of the box, you can do all kinds of cool fun checks to it. Some of the ones I really like here are like the vuln generic environment. So we'll connect to an S8 session. We'll shake out a session one way or another. You can give us a password list. You can give us a bunch of private key. You can give us a public key. However you end up getting a session, whether it's through a bypass or not, we'll then try all these other attacks on the session itself. So before we open the session, we'll set like LD debug equal all. We'll set LD preload. We'll set all these other variables. And then we try to like dump out output to see did it actually work. And we got some good results. We just finished like a 70 gig JSON dump of local internet and SH with this tool. So we'll share more about that later, hopefully. But we need to dig through all the data still, like little data raccoons that we are. And yes, you want to talk to anything particularly you want to highlight?
Do what?
Anything you want to highlight particularly?
Oh, no, this is all just some fantastic stuff. I love it. So the way it works, you can do a network scan with Shamble, and you can give it an IP address or a range, a CIDR, and it will just tell you, it will go and scan, try to find SSH, try to find any vulnerabilities, try to find any ways that you can get a shell, things like that. You can also run the analyze command, which will actually, you can take one of the JSON dumps, and like HG said, they can be quite hefty, and run stuff like that. You've got all of the vulnerabilities that we mentioned are built in, and you can actually say, oh no, I'm vulnerable to this, or I'm not. And then the interactor shell is fun. That's your
okay.
You should
so
take it.
One of the things that's really annoying in SH to test is like, how do you do all these attacks against the SH environment before the shell is spawned? And it's really annoying to do that. You can use Paramiko, you can use some stuff like that, but like we decided we need like a nice interactive shell instead. So in Shamble, by default, it'll just like request a PTY, request a shell, give you the prompt, let you do whatever you want to with it, and then you can do commands on top of that if you want to. However, you can do session interact equal nothing, and it'll open up a session, but not actually start the shell yet. And that puts you in what they call the larval session environment, where you can do all kinds of fun attacks prior to the shell even starting. So if you get into like a net screen box, for example, it'll actually let you authenticate as nobody. It'll give you this weird empty shell, and it lets you like send whatever commands you want, but it doesn't really give anything back out. So that feels like a really ripe attack to go find ways to knock out some NetScreen bugs, because we have a session, it's doing something, but it's not quite a shell yet. So there's a lot of different embedded devices and custom SSH implementations you can mess with like this. A lot of Windows-based SSH daemons, I think like Core FTPD, maybe a couple other ones, maybe it's Crush, I forget. But they allow you to basically get a session that's not really a real session yet, and then you can use the Shamble command line to start messing with it and do all kinds of fun things with it. So this is great if you need to like, backdoor something. You see a lot of like appliance vendors, they ship you an appliance as a restricted shell. This is a great way to start attacking those restricted shells. Cool, and with that, happy scanning, and we'll talk a little bit about defending SSH to be responsible adults.
Thank you. Yep. Defending SSH. There's a little bit left. There's a little bit left. I got 2 minutes. So just real fast, I wanted to make sure that I wanted to leave y'all with some action items on how you can improve your SSH security posture. So for one is, make sure you're not using, make sure you're using public key authentication. Don't use passwords. Don't use auth none with left beef. That's bad. And if you're using the SSH agent, be sure that you add as many restrictions as you can. Be sure to use only modern encryption algorithms, especially now that post-quantum is the new thing. With host keys, actually manage your host keys. Make sure that you are not handing them out to just anybody. Make sure that they are, in fact, not duplicated. Use modern public key authentication with stuff like ed2 5519. I always want to say ed209 from Robocop, but it's not. Make sure that you are turning off. So when you use the public key authentication, you can even say this key is not valid for X11 forwarding or agent forwarding or things like that. So be sure to turn all that off as well. And you can also do things like using forced commands. You can use certificates for server host keys, which lets you actually just distribute a certificate and then the host key can be signed. And you can also use that for public keys, which I've done some really amazing stuff with that in a past life. That's a lot of fun. Highly recommend reading up on that. It's kind of the hidden secret of how awesome SSH can be. And then if you're going to use SSH, I'd recommend sticking with OpenSSH. It tends to be have the most security features. It tends to be the most tested, obviously. Don't ship firmware with embedded credentials. You would think that would just be kind of a thing, but no, that's something that we need to say. And use force commands, so when people SSH in, if they're only supposed to do certain things, you can say, OK, you really only can do certain things. But with that being said, the secure shell is everywhere. It is the default de facto admin protocol of the internet. You should use public key authentication, but it can be leaky. OpenSSH is still your best choice. And there's still lots of issues in the periphery. There's still that long tail. There's still sort of the hidden things that you might have forgotten about. So thank you so much. Please check out runZero.com. You can email us at research@runZero.com and go to shamble.com to check out the tool. Thank you so much for coming.